Hello and welcome to Lesson 6.5, Intersections of Lines and Planes. These are the three different ways that a line and a plane could interact in three-dimensional space. In our first case, you can have one solution. That's where the line is going to intersect the plane at only one possible point. In your second case, you can have an infinite number of solutions. This occurs when your line actually lies inside the plane. And in your last case, you can actually have no solutions. This occurs when your line is parallel to the plane. What we're going to do is we're going to take the parametric or vector form of a line, and we're going to take the scalar equation of a plane. We're going to substitute them because the x, y, and z values need to be the same. And we need to see if it actually gives us a value of t in our equations. So in our first instance, what you're going to usually get is a number times your variable t equal to a number, which you can solve. For infinite solutions, what you'll get is a value of 0 times your variable t is equal to 0. This occurs when all your values of t are possible. And in our last case, what you're going to get is 0t equals some number other than 0, which shows that you can't get any possible values of t possible. Okay, so again, to determine the points of intersection, what you want is your line in vector or parametric form. You want your plane in scalar form, and then you're going to substitute the values inside. Now you can always use the normal and the directional vector to see if the plane and line intersect, but it's not really necessary to actually go through. You're actually going to find this solution out anyways when you do this complete substitution. Okay, so let's try it. So for this line, we have the vector 1, -6, -5 is my starting point, and my directional vector is 2, 3, 2. So what I'm going to do is, using my line, I'm going to write it in parametric form. Then I take that line, substitute it into x, y, and z. From here, you want to expand and simplify and solve for t. Okay, so it's going to be 4t. Using my calculator right now, just to work this out. This one turns out to be -8. So here you get a t value equal to 2. So if our t value is equal to 2, that means you can substitute back into your parametric forms and actually find your point of intersection. So your x value is 5. Y value is 0. And your z value is -1. So therefore, a point of intersection is 5, 0, and -1. Okay, let's try that again. So I encourage you guys to pause your video right now and try this out on your own. Okay, so let's see how this works out. So for our line, parametric forms are 2 plus 3t, negative 3 plus 1t for y, and z is 5 minus t. Okay, so now I'm going to take that and I'm going to substitute it into my scalar equation. Okay, again, expand. Like so. I'm going to use my calculator. So I get 0t in this case. And this is 0. So 0t equals 0. That means t can be any value, and therefore infinite solutions. The line is inside the plane. You don't have to go any further and actually state the line again. You can just state that the line and the plane intersect in infinite solutions. Okay, so what we can do now is we can use materials from last day to help us actually find the distance from a point to a plane. So how do we do this? Well, if our plane is given by this equation, which we call x minus 2y minus 2z equals 6, we know, equals negative 6. We know the normal coming out from this plane is 1, negative 2, negative 2. The point, negative 6, 4, 5, I'm going to assume is out in three-dimensional space some point. And we just want to find the distance between those two. Well, what you can do is find a point that's actually on the plane, which you can call your points P and Q. Then you can take that PQ and project it onto the normal to find its length. Again, just like we did before. So in this case, I need to find a point Q. Easy point for point Q is just negative 6, 0, 0. Just using an x-intercept here. Okay, so I have to figure out my vector PQ first. Oops, 0, negative 4, negative 5. Okay, so now to find out my distance, I'm again using the same formula that I did from before. To solve. Okay, so this works out to be 8 plus 10, which is 18 in the numerator. Absolute value of that is just 18 still. Denominator turns out to be square root of 9, which is 3, so D equals 6. Now, it's just coincidental that there's a number of values of 6 here that work out. So, distance between the line and the plane is 6 units. And again, it doesn't turn out to be exact like this all the time. And this concludes this lesson.